Hello, everyone, and good evening from Savannah. Welcome to the July presentation of An Evening at Skidaway. I'm Dan Onimus, your disembodied host and moderator this evening, and our speaker tonight is Dr. Catherine Edwards. Dr. Edwards is a physical oceanographer and a specialist in the use of underwater robots to study the ocean. By way of academic credentials, Dr. Edwards earned her bachelor's degree in physics from the University of North Carolina at Chapel Hill, and her PhD in physical oceanography, also from UNC Chapel Hill. Tonight, she's going to tell us about those underwater robots and the way she and other scientists are using them to track fish. So Dr. Edwards, take it away.
Dan, thanks so much for the kind introduction. I'm really excited to talk today about a project I've been working on with collaborators and students for the last 2 or 3 years. I joke and jokingly call it Alexa map fish habitats. But what we're doing is using artificial intelligence for robotic fisheries management. And it's highly exciting and highly interdisciplinary work with a large number of partners, many of which are listed here. I'll acknowledge a lot of the people on this work, including Frank McQuarrie, a PhD student working with me and Brock Woodson at UGA in engineering, as well as a number of students working with Fumin Zhang at Georgia Tech, some students working with Xiaobo Tan at Michigan State, and then students working with Mike Cox at Wright State University. I'd also like to acknowledge former students who'd worked with me and Fumin Zhang through Georgia Tech, as well as collaborators at Gray's Reef National Marine Sanctuary, Sarah Fangman, and more recently, Kim Robertson and Allison Sauce. So for those of you who aren't familiar with Gray's Reef National Marine Sanctuary, it's a marine protected area. Think of it as a national park for the ocean, about 40 miles off away from Savannah. It's 22 square miles in terms of area, and its average depth is about 20 meters or 60 feet. When you look at Gray's Reef, you see on the bottom, there's large grained carbonate sand, but popping out of that sand are these submerged hard bottom pieces that have ledges that stick up. These ledges form habitat to over 200 species, including corals and fish, invertebrates and turtles. So in looking at fisheries management at Gray's Reef, one of the tools that fisheries managers at NOAA use is called acoustic telemetry. This is using sound to follow fish and other animals around. The idea is you take a tag with a known frequency and you either implant it in or stick it on an animal of your choice. And then by using receivers around your area of study, you can detect where that animal is. Basically, at regular intervals, the acoustic tag transmits a unique acoustic signal that includes what the animal is, or I'm sorry, it includes a signal that is a code for what that animal is. Then those tags, those detection beeps are then picked up by receivers that are acoustic hydrophones that decode the transmission, get the tag ID number and adds a date or a timestamp. Then fisheries scientists all over the country and all internationally can collect this list of detections and contribute it to regional and national detection databases, where you may know only what tag numbers you used on your fish, but by collaborating on the regional and national level, you can find out the tag numbers and the identity and the dates that those other animals were tagged. Now, this technique is used in fisheries management for a number of reasons. One way people at Gray's Reef use it is to think about habitat use and monitoring. What parts of the reef are being used by different animals? There's also an estimate of reef fidelity. How much do animals congregate over certain parts of the reef and how much time do they spend there versus leaving and coming back? And it's also used to think about connectivity. Are individuals in Gray's Reef making migrations or moving in between the inshore environment and Gray's Reef or offshore out to the Gulf Stream? What are those connections between populations around in space? In long distance cases, it's also used to look at migrations, where animals that make long distance migrations all the way up and down the East Coast make their way through Gray's Reef National Marine Sanctuary. And so that data is able to help the scientists understand where those animals are moving and how. And then lastly, an estimate of how likely animals are to return to a reef once they've been there. So these are all fabulous tools to use, and the way that a lot of fisheries scientists use them is to have static hydrophones, have these receivers and use them as range gates. So anytime a fish passes by, you'll be able to hear the detection, hear the ping as it goes by, and know kind of if you're close enough that something was in your reef or in your study area. The problem with this is that you have to be sufficiently close to whatever animal is tagged to be able to hear it. And you don't necessarily know that information in advance. And since the ocean is really, really big, there aren't enough hydrophones in the world to be able to know an absolute network of where all the tagged animals are going. So then autonomous underwater vehicles become really attractive as a way to monitor acoustic telemetry on a mobile platform. So I use autonomous underwater vehicles, and one of the ones that I use are called gliders. They measure temperature, salinity, oxygen. They can measure organic matter, backscatter, and chlorophyll as well. But they also can be integrated with fisheries management tools like acoustic telemetry receivers, echo sounders like a fish finder that bounce sound off of animals and can get a return from individuals or schools, or passive acoustics that can measure soundscapes, whatever, sort of like a microphone in the ocean. Gliders are really attractive platforms for acoustic measurements because their major method of propulsion is fairly quiet. They move not with a propeller, where you'd have a lot of noise from that, but they move by changing their buoyancy and center of gravity. By moving an internal battery forward about an inch, the glider gets pitched down, and it sucks in a volume of water to make that nose heavier, so it uses gravity to fall to the bottom. Wings on each side give it lift for horizontal motion. And then at a certain distance above the bottom, the glider reverses the process. It pushes out the water so that it's light. It moves the battery back so that it's pointed up, and it comes closer to the surface. So in that way, it's moved up to a football field or two, depending on how deep the water is. And at regular intervals, it comes up to the surface to transmit a subset of the data that it's collected. It's also really attractive because it's a chance to interact with the robot, to be able to see what the robot is seeing, see the data that the glider has collected, and potentially adapt its path over time. So these are a really interesting option if you're going to design a robotic network using gliders. Let's think about what we would need to do that. So that's what the talk today is going to focus on, is an integrated robotic network design specifically for Gray's Reef National Marine Sanctuary. In general, when designing a network, you need to think about the goals and then the challenges, the choice of robots, and then in our case, how we're going to adapt how the network functions to environmental variability. And then lastly, I'll wrap up the talk with some discussion about goal-based decision making. How do you balance sometimes competing needs to control the entire fleet and stay flexible but robust? So, when you're designing this robotic network, ultimately what matters is the fisheries management. Those goals that I pointed out earlier about reef fidelity and monitoring populations. For Gray's Reef's concerns, they'd like to use the network because it would mean a reduced need for dive operations, which are personnel intensive. And over the past year and a half or so, they've had limited capacity to have dive operations due to the global pandemic. The robotic networks can also be long endurance, and they want something that's long endurance, low cost, and then sustainable. How much effort does it save if you're switching out robots all the time? And then lastly, one of the wishes from Gray's Reef and other MPAs is a flexible system. Gray's Reef is particularly interested in ecological connectivity. So how could you use a system both within Gray's Reef and then leverage these same tools outside of the sanctuary to look at population connectivity questions? The considerations in robotic network design can be considerably different from the perspective of robotics. One of the primary goals of robotics in this type of system is to reduce the human burden on both operations and planning. We have a number of people who pilot our gliders for Skidaway and as part of regional association work. And any glider pilot will tell you that they wish that gliders were a little more autonomous sometimes. There can be a lot of troubleshooting to interface with the gliders and with any autonomous underwater vehicle. We also want to enable longer and multi-platform studies so we can look at multiple scales at once. And then from a scientific perspective, from the robotics perspective, we want to maximize the value of our observations. As a scientist myself, I've got some really fun questions to think about for Gray's Reef in terms of how the tides and stratification interact, how do rivers and tides and winds interact in Gray's Reef, and how does that change nutrient availability or cycling, and what does that mean for the actual science of the fisheries? But basically, sometimes these needs are competing, worse, sometimes the language that scientists use, we're all specialists. The engineers and the roboticists and the oceanographers and the fisheries managers are specialists in our own field, and we don't necessarily have the ability to translate what the goals are for each of these components: science and engineering and robotics and fisheries management. So artificial intelligence can serve as a bit of a web in which these goals and needs from each of these communities are translated and then turned into basically a big old to-do list that's optimized for the goals of the actual fisheries managers. What are the outcomes scientifically? And then in thinking ahead to Gray's Reef, I mean, we want this network to be robust. We also want it to be flexible. We want it to be able to adapt to challenges that come up. And since we're familiar with Gray's Reef, we can also think ahead to some of the challenges at Gray's Reef. One of the challenges I've nicknamed the hunt for Red October. When using acoustics in Gray's Reef, it is a really difficult acoustic environment. If you remember the movie The Hunt for Red October, Sean Connery is the bad guy hiding in the submarine, and he takes advantage of the change in sound speed and sound channels in the ocean to hide from the Americans who were trying to find him with pings that travel acoustically through the ocean. And it turns out, because sound speed varies as a function of water temperature and pressure, a little bit due to salinity as well, the medium through which the sound wave progresses actually changes the sound. You end up with a refraction of the sound wave as it moves through space, moves through this medium, these changes in temperature, salinity, and pressure. So that's what Sean Connery was leveraging here. He was hiding under the picnic line because the sound couldn't get to him. In complicated places like Gray's Reef, where the acoustics are not straightforward and the water is shallow, and there's a lot of physical processes, you can be very close to a tagged animal and not be able to hear it because of the physical oceanography and how that in physical environment varies in space and in time. This is something we learned recently through an experiment we did in 2014. We basically made up an obstacle course of receivers at known locations with reference tags tied to a buoy above them underwater. And by downloading the data and knowing that the receiver was staying in one place and the tag was staying in other, we could look at the time variability of how many detections you got as a function of time. So this upper panel goes over 2 days in September 2014, and you can see the number of detections per hour go from 0 to about 30, which is a little less than half of the number of pings that the tag put out. And that over this course of 12.42 hours, it goes from about 40% detection rate to about 0. And this repeats at about 12.5-hour intervals that correspond to the tide. The lower panel here shows the currents that we measured with a nearby instrument, where the blue lines pointing in this direction point to land, and then the tide moves around. When the tide is pointed to land, we end up with the highest number of acoustic detections. And when the tide is pointed away from land, we have the lowest number of detections. It turns out we can use glider data to see how much the water properties change from surface to bottom, how much temperature and salinity affect density, and how that changes the density from the surface to the bottom, called stratification. And those times of the maximum detections efficiency correspond to times when the water column has low stratification. So it's well mixed. The temperature and salinity and density are similar from top to bottom. But when there are larger differences in temperature and salinity or density or all three, you end up with a reduced ability to detect. So what this is telling us is that the acoustic waveguide, how these sound rays move around the water column, it changes each tidal cycle. And so therefore the detection range of these tags changes as a function of time, and it turns out of space as well. So you can think about gliders flying around with these acoustic telemetry instruments built into them, and they're listening for tagged fish and reference tags. Each of the fish with a tag in it has a three-dimensional volume of detectability. If it were just a range that was a straight number, it would be a sphere. In all directions, it might be 400 meters. But our work has suggested that it's not spherical at all, that it's very compressed in space in the vertical dimension, and that as a function of time, it gets larger when the water column is well mixed, and it gets smaller when the water column has large temperature and salinity differences top to bottom. So what happens to get a detection on this glider, you need for the sphere around the fish or the reference tag to intersect with the three-dimensional volume of detectability around the glider. Only then will you get a detection. So here's an opportunity to leverage what we know about the physics and the physical oceanography at Gray's Reef with tides and wind, but also the data from the glider to estimate how large these volumes are and how much may they change in space and in time. In terms of our robots for this network, we're using gliders as our primary instrument. These gliders have a number of sensors involved, but for our purposes here, we're looking at the combination of these integrated acoustic receivers for acoustic telemetry. There's one on the surface and one on the bottom of this middle section, the science bay. And then on the opposite side is a CTD that measures conductivity, temperature, and depth as the glider moves up and down. So those give us real-time estimates of what the temperature and salinity profiles are that we can use to then calculate sound speed. We also can collect the fish detections in real time and pass those back to shore. What we want to design here is a dense and flexible cooperative fleet with one or more robots. But depending on how that detection range changes as a function of space or time, we may need to change the spacing or how we move those robots around. The other robot we use in this work is a robotic fish designed by colleagues at Michigan State University, Xiaobao Town and his group of students. These robotic fish move both by gliding like the gliders do, but they also have the ability to move with a bio-inspired tail motion. The key thing here, and the key thing for this robotic network, is that they're very low cost. The fish themselves only cost, they cost less than $10,000 to build. Sensors then add more on top of that. So these things are scalable. While the gliders cost a lot more than that, they cost in excess of $200,000 each. You can embed gliders into basically a school of robotic fish that are flying around. These fish can communicate to shore, but they can also communicate to other fish. And then they've got some advanced capability with an onboard processor that lets you integrate some advanced autonomy techniques on board the instrument itself, instead of having to call back home. So our smart and autonomous system, our robotic network, is starting to take shape here. We have a school of robotic fish here, and we have some real fish that have been tagged. We also have some reference tags that we know won't change in space and time, like the robotic fish and the real fish do. And then the robotic fish and the gliders are outfitted with these acoustic receivers that can hear the tagged fish, they can hear the reference tags, and they can hear each other. Then the glider data is able to be used to estimate that detectability around each of these. So we can adjust our network based around real-time conditions and environmental data that come back to shore. So here's where the artificial intelligence comes in. Artificial intelligence is everywhere. You may drive a car with AI built into some of its functions. You might have a Roomba that vacuums and it takes advantage of AI in its control. If you're watching on YouTube, there are AI techniques used that might help predict what kinds of videos you might like to watch next. And it's often presented in these sort of scary futuristic kind of diagrams that look very, very technical and futuristic. But it comes down to a few principles. One is of learning and sensing and identifying patterns from data. Some of this can be on the fly, and some of it can be from training that's sort of set up in advance. There's AI measures to connect these to connect one instrument to others and connect patterns to other things. There's a lot of AI work and interpretation of what a robot can see, or what interpreting it, what intent a data stream has. And then understanding what's the cognition that happens from these patterns. So what we're doing here is we're using artificial intelligence as this web with which we connect various parts of our network. Each of these methods basically can often be described in terms of two major ways of thinking. One is a deterministic thing that says, if the Roomba hits something, then we should turn and move in a different direction. And that's the best way to control your robotic vacuum. If this, then that. If you see this, then do that. The other way of thinking about it is what is the probability of different outcomes? So it's a more probabilistic method of AI, where you might see incoming data and say, well, I've hit something. Is it likely to be a chair leg, or is it something new? Am I about to fall off a cliff? So we integrate both types of these decision-making into our robotic network. I'm going to focus here on some of this probabilistic approach because we're going to be able to use the glider data and turn it into a map of probability of when and where we're likely to hear fish, and then use that as a tool to adapt our network in response. So this is a very simplistic view of the integrated robotic network we've built for Gray's Reef, where we've got this web, think of the background as your web, and a number of agents that each collect a bunch of data that we feed into models, and we try to understand how much uncertainty is available in those models. We feed those into map making tools that we use to automatically identify likely hotspots because of the probability, which is given here as a function of space. And this will again change in time. With this input into the larger decision-making system, you can come up and evaluate strategies that find the cost of doing the work and and minimize that cost by choosing the strategy that's most efficient or that meets your goal the best. We also want to evaluate the hazards and different strategies for how we might adapt our network based on our inputs. Lastly, we want to take all this together and assign fleet tasks where, hey, this fish, you take that section of the reef and go measure this hotspot. Then lastly, we want to help understand when the system, when things are going sideways. This goes to robustness. So we want to detect faults or anomalies and then have strategies either built in or learned for how to adapt them. At the moment, we're building in those alternate strategies. In the rest of today's talk, I'm going to focus on this bottom half of this sort of larger map. Simplifying it even into a flow chart is way too simplified because of all of the cross connections of the components. But basically here, what we're going to focus on is using the data from the glider and the robotic fish and the information we sense from the environment and building models and uncertainty estimates that help us make maps, but also help us develop strategies for moving the instruments around. This is some work, some of it very hot off the presses from a PhD student working with me and Brock Woodson, Frank McQuarrie, who's a PhD student in engineering at UGA. We have a library of acoustic data from a NOAA-funded experiment in Gray's Reef in 2019 and 2020, in which we deployed a glider in Gray's Reef around a series of stationary receivers that had a number of hydrophones that measured also the background sound as well as the acoustic telemetry. So as the glider moved around this static array, we can hear when each of these receivers is, we can detect them. And so you can see a little X pops up in the circle when a detection is heard. And if you look closely, the glider often goes near a receiver, but it may not be detected. There's other times when it hits right on and from a farther distance than you'd expect. Frank has taken these deployments and mapped them. This is just for 2020 here on the lower left-hand side, that shows the amount of time. You take all of this, the science area at Gray's Reef, and you break it into blocks. And you can see how much time is spent in each of these blocks. And that's represented by the colors here in blue, where the darker blue, the more time is spent in that box. And the lighter the color, the less time is spent in it. Those data are then used to scale the number of detections that are measured by each of the receivers that are indicated by the little box, with a percentage that is a detection efficiency that's based on the number of detections over the amount of time spent within 1 kilometer of that receiver. And straight away, you can see that the detection efficiency in some parts of the reef is far less than in some others. In fact, on the offshore side of the reef, you have 2 or 3 or 4 times greater efficiency than the receivers in shallower parts of the reef. What we want to do is use the data to estimate what the acoustic range is of these tags and receivers and how that changes as a function of time. You can take this library of data, and in fact, Frank has taken this library of data and looked at that detection efficiency as a function of distance from the actual glider itself. Whereas the prior view was fixed in space, this one is following the glider. And the time spent in a certain amount of the range is here shown in black. And the detection efficiency, which is scaled by that time spent, is shown in 3 different colors: for the 2020 experiments in red, for the 2019 experiment in blue, and then the overall efficiency as a function of range. So this is a tool we can use in the average to inform the network about how far away in general can you hear a tag based on prior work, based on real observations. But can we predict that over short timescales? So this is our setup here, where the glider is flying around. It comes to the surface every 4 to 6 hours, and it reports its data, its temperature, its salinity, and its pressure as a function of depth here on the y-axis over this 4-hour surfacing interval. These data come in real time, and we can convert those to sound speed profiles computed from the temperature, salinity, and pressure. Those we can feed into an acoustic model called bellhop, which basically takes a whole bunch of acoustic rays at a set depth. We're using a sound source at 16.5 meters, which is a reasonable representation of reef-dwelling fish like snapper or grouper, being a meter or 2 above the bottom, shooting sound out in every possible direction and seeing how it propagates. Some rays hit the surface and then hit the bottom. Some of them never make it to the surface. Some of them sometimes hit the bottom. And you can count as a function of distance away that these rays make it, fewer and fewer rays make it farther distances from the sound source. Frank then takes these number of rays and basically counts them up as a function of distance to come up with a detection efficiency from the model. We can then compare it with our observational estimates to make some tweaks into what fits with what has worked in the past, or maybe even what has worked recently, and come up with this short-term forecast over the next couple hours for the network to use. This information can then be passed along to all the robots in the network. We can see over time this changes, this probability of being detected at certain ranges changes as a function of time. I've plotted here, or Frank has plotted here, 3 sound speed profiles. The red case, where the water column is fairly well mixed and the detection ranges are quite long. You can hear this sound source at longer distances than in the blue or the black case, where there are changes, these bends in the sound speed will cause refraction and change the way the sound waves are propagated. This effectively lowers the distance for the detection range. So this is the fun part then. How do we leverage that information? One way is we put it into the artificial intelligence framework, and we can build hotspot maps by taking the data in real time, where this is a glider or a robotic fish, and it might hear these things within this radius that's set. In this simulation, it's set at a set value. But we can have that radius change as a function of time based on the data we've collected. And then these data over time are used to create hotspot maps that basically show where the highest probability is of fish. We can use this same data also for our choice of search algorithms. Instead of having multiple robots work on lawnmower style grids, when the water column is well mixed and the detection ranges are farther, you might change your spacing of the robots. And then when there's larger differences in temperature or salinity closer to the surface, your detection range is smaller, so you change the behavior of your fleet of agents. We also use this data in path planning. But ultimately, these are larger parts of a system that reasons goals. It says, what is happening? How am I assimilating this information? What are the strategies we need to do? And then tasking it out to each of the components of the network. This is done through some software developed by my collaborators at Wright State University, Mike Cox, and students who've worked with him. The software is called MITCA, or Metacognitive Integrated Dual Cycle Architecture for Self-Regulated Autonomy. This is software that can be built onto the robots themselves, onto the robotic fish, and then we've integrated it in within our path planning as well. The neat thing that Sravya Kondrakunta and Sampath are working on with this software is fault or anomaly detection, where there might be some areas when a robot realizes it can't make it there. How does the system recognize that and then retask the agents to adapt the whole robotic network to what's happening in real time? This is some of that recognition and decision-making that happens, but at the top of all of these goals is actually the fisheries management, who is the ultimate, I guess, customer of this work. So what we've done is we've talked about an integrated robotic network. I really wish we could have dived into more details about how these pieces interact. I kept on trying to make flowcharts that were simple and realized it was near impossible because so many of these pieces work together and there's inner and outer loops of optimization. But ultimately, it's driven by the goals of the fisheries managers in understanding where these hotspots are and adapting to the environmental conditions. This robotic network characterizes environmental changes in detectability and responds to it. It predicts what's happening and going to happen in the future. And then all of the decision-making is made through this multi-level planning tool that kind of sees all of the things that are happening at once and then pulls the strings as needed. It's tailored for Grace Reef, but it's highly adaptable to other problems as well. You know, we went into this problem knowing that there were some issues with the detection range changing due to the tides, and then they change because of the seasons. But in other places, the acoustic environment may be different. So any or all of these aspects can be tweaked and tailored to other places, adapted for other places. We're also interested in some really fun extra credit work that amps up the connection with the actual fisheries management. Here is a map of the receiver array used in the Soundscapes experiment in 2019 and 2020. Each of those dots represents another of the receivers that we used. And the bottom type in Gray's Reef is marked by the colors. The blue colors represent live bottom, either densely or sparsely colonized. And then the kind of more orangey tan colors represent sand, areas that are flat, that are shown in the orange, and then rippled sand shown in sort of the tan color. We know that acoustic propagation changes with what type of bottom there is. So you can think about a ray of sound hitting a rock, and it'll reflect differently than it might, or act differently, interact with the bottom differently than it might with sand or mud or different types of bottom. So it'd be really cool to build this into not just a 2D, but a 3D map of Gray's Reef, where we're mapping the three-dimensional acoustic environment with bellhop in 3 dimensions and integrating these different bottom types. Lastly, there is a long history of fantastic science at Gray's Reef National Marine Sanctuary, including surveys in different parts of Gray's Reef for different species of interest, like scamp or gag grouper and black sea bass. And this work has showed that the distributions of these animals are different. There's some parts of the reef that certain species like more or are more or less likely to be in. These are distributions that turn into probability maps, the same way that our acoustic models gave us probability of being heard within a certain radius. So it would be really fantastic to build this species-specific knowledge or guidance into an intelligent robotic network to even greater highlight the needs of the fisheries managers. I'll stop here and re-acknowledge all of the fabulous collaborators and the wonderful group of students, graduate students who've worked on this project. There's a weekly meeting of all of the graduate students together, and I think they're having a lot of fun integrating the various pieces together. As well as the people who've contributed to this work over the last 8 years or so. So with that, we'll stop for questions.
Great, thanks, Catherine. I guess I'm the only other person on this Zoom call, so I will give you some applause. And we'll wait for some questions to roll into the chat. Thanks a lot. I have a couple of questions lined up from beforehand, if that would work. Where's my notes? Okay, I was curious, how many gliders does Skidaway currently have? And sort of a second question, are they always listening for fish while they're on missions, or can they do it while they're doing other operations, like other programs?
So I'll start with the second question first. Is okay. We can do everything at once. So with the gliders that have integrated acoustic receivers in them, those are built in, and it's just a matter of turning them on and off. Awesome. They do not interfere with other sensors on the instrument, so it's sort of free data. Great, we'd love to pass this along to not just our friends at Gray's Reef, but regional collaborators all over the Southeast Atlantic and our national networks as well. At Skidaway, we own one glider, but our stable is full of gliders that we operate for other institutions. We currently also operate a glider for the Sakura Regional Association, the Southeastern Coastal Ocean Observing Regional Association, as well as gliders from University of North Carolina at Wilmington. That's Pelagia. She's going to be recovered tomorrow off of North Carolina. And a glider that's owned by North Carolina State University.
Oh, that's great. There's no enterprise rent-a-glider quite yet, huh? Maybe in a couple of years?
Not yet, not yet. We can work on it. We get a lot of visiting gliders through our fleet. We do regional work where we deploy or recover with partners as well.
Oh, that's great. Some folks are wondering, do you have a favorite of them?
Oh, these gliders, they're so it's so easy to personify them because they have names: Angus, Franklin, Pelagia, Salacia, Ramses, Sam, Stella. All of them are lovely. They each have little personalities, and because they talk to you, it's really hard not to think about them that way and anthropomorphize them. But Angus is our Skidaway glider right now. He's been a beast, and so we're glad to have him go out for our next mission at Gray's Reef. He's the primary glider for this project. We've got some new instrumentation to use on him as well.
Cool. There's a question here about when they come to the surface, so every few hours. Are there boats around to protect it, or is it something that's being actively protected from damage by other animals or boats or things like that, or is it just entirely sort of luck?
It's unfortunately just luck. The ocean is really big, and a lot of times we rely on the ocean being really, really, really big to prevent danger. The other thing we do is we minimize the time that the glider is at the surface. So in that 4 to 6 hour leg, we're at the surface some amount of time between like 8 and 14 minutes. So this entire transfer of knowledge of the glider coming up and saying, hi, my name is Franklin. I'm at the surface of the ocean. This is what I'm doing. Here's a subset of my data that we then use. We make plots, we calculate sound speeds, and then we tell the glider what to do. That all happens over a span of less than 15 minutes, which is pretty powerful.
Oh, that's great. Question here. So what's the main impediment to increasing the number of measurements in Gray's Reef? Is it the knowledge of the area, like mapping like you were saying at the end, or is it more like a cost thing, like the cost of the tags or the number of gliders or references?
Well, it's a number of things. You'd love to, as a scientist, you'd love to increase the density of observations in all of your favorite areas of study, right? What part of this project is figuring out, based on the environmental data, how many robots does it take to actually understand how many fish might be in certain areas? Okay. So it's just figuring it out on the fly. That's a really cool robotics question, but it's also interesting for management purposes, especially knowing that may change in wintertime. You may need fewer of those robots.
Right.
Yeah. I wish we were in the position of deciding, oh, we don't need as many robots, because the ocean is really fundamentally undersampled. Even our favorite places like Gray's Reef that have a number of instruments in at any time, listening for tagged animals or listening for soundscapes, or like the gliders, which are at Gray's Reef about a couple months a year these days, measuring temperature and salinity. In talking with Gray's Reef, it'd be fun to keep gliders there all the time so that you can take the data from the gliders and combine it with the data that you get from stationary networks of receivers. And you can't get rid of that diver data. It's super valuable way to observe the ocean firsthand and be able to put together those trends with what you can get from stationary or robotic networks. It's a different kind of network of observation.
Yeah, you mentioned the winter time. Is Gray's Reef noisier during the winter when the surface of the ocean, I'm guessing, is like choppier and windier, or is there any big seasonality to the noise?
Yeah, noise changes all the time. Gray's Reef is a noisy place. You get tons and tons and tons of snapping shrimp. You hear the sound of boats every now and then coming in and out of Gray's Reef. And actually, that's one thing that the sanctuary is really interested in. How often does traffic go through Gray's Reef? And just like national parks like to track the number of visitors, marine protected areas want to be able to track the number of visitors as well. Another visitor we get off of the Georgia coast and in Gray's Reef are right whales. So some of these instruments can be used, particularly the hydrophones can be used to measure the sound, the general sound of right whales as they move through. And we're working on techniques to be able to say, hey, this glider just heard a whale, let's tell somebody about it, and fold these types of tools into networks as well.
That's really cool. Are there ways the public can interact with them, like listening to them or things like that? Are there public outreach sites for that?
Yeah, we do a lot of public outreach through Gray's Reef National Marine Sanctuary. We have programs for high school and middle school students that we've run for the last several years through the Society of Women Engineers, Girls Engineer It Day, and a program that this year we ran virtually via Zoom, but we'll be returning in person for Savannah area girls from 6th to 12th grades. We'd love to be able to integrate some of these soundscapes into exhibits at the museum, and then downtown displays so that people can see what's happening at Gray's Gray's Reef, while you're not looking at it from shore, you can listen to some of the sounds. All of the data that we get from the gliders is shared in real time with national networks that take in profiles of temperature and salinity and use it to improve models for predicting things like hurricanes. But also we share our detections of fish and other animals with these regional networks as well. We're working on improving some of these sound samples so you can hear a little bit of what Gray's Reef sounds like. It also turns out that gliders aren't quite as quiet as you hope they are. They make a little bit of noise themselves. So that's really fun to hear. It's also potentially useful information to use in some of these robotic networks as well.
Excellent. That's all the questions I have from the chat. If there's anything you want to add, feel free. But otherwise, I think we have a list of the schedule for the upcoming talks as well.
Great.
Great. So thanks again, Dr. Edwards, for that great talk. The next event on the Skidaway public outreach calendar is an Evening at Skidaway open lab night, which is a different date from the original schedule. So if you have the printed copy or the refrigerator magnet, bring a Sharpie to it and change the date to Tuesday, August 24th at 7 p.m. Several Institute labs will be open, and you can visit informally with the scientists and check out our research and ask plenty of questions and bounce around. So looking forward to seeing you in person. It'll be our first in-person event in quite a while. So we're all looking forward to it. And then after August, the rest of the schedule is shown here. Dr. Clark Alexander will give us a look at earthquakes and tsunamis from his research and other talks that are listed here. So looking forward to seeing you all in person and getting back in the lecture hall and into the labs to see everyone. So thanks a lot, and thanks for joining us.